everyone, welcome back to Exam Ignite. We have already covered the first part of the Module 3. If you haven't seen Module 3 Part 1 yet, the link is in the description box. Make sure you watch it first. In this video, we will be continuing with the remaining topics of the Module 3 of Principles of Communication System based on the VTU syllabus 2022 scheme 4th semester. So as I have said earlier, this is a notes that is referred, handwritten and referred with the syllabus textbook. Model question paper 1 and 2, VTU exam question papers Jan 2025 and July 2024. So this is a handwritten notes which helps you to focus on the important things for your preparation. So let's begin with the module 3 part 2, that is FM circuits. FM circuits, in that frequency modulators. Frequency modulation varies a carrier signal in response to the message signal. Carrier is generated using the LC or the crystal oscillator. We are having two cases. So frequency variation is achieved by changing either the capacitor or the inductor. So this crystal oscillator, they have a fixed frequency but slightly tuned using the extra capacitor. So main objective is here to vary the capacitor based on the modulating signal. So here we will be using a varactor diodes. This is an important topic you need to know. This is an voltage variable capacitors used where it is in the form of this, and here we are having a diode along with a capacitor. This operation is based on the reverse bias junction. So for your clear understanding, I have written the depletion region acts as an insulation. This is what our PN junction. P with the positive and N with the negative ions. So here in the forward bias, what happens is the positive charges are repelled by the P junction and the negative is repelled by the N junction. So this gets closer and there will be no any widen area. It will be a narrow region. But when it comes to the reverse, that is when there is a negative here, the positive of the P get attracted, and for the positive of this side, negative gets attracted. So this widens the region. This is called as reverse bias. But here in the varactor diode, we observe it is based on the reverse bias junction of the diode, that is this case. So here PN regions are the plates of the capacitor. So depletion region is dielectric. Wider means it is having low capacitor, narrow means it is having high capacitor. Capacitor will range from the 1 to 200 picofarad. Variation is up to 12:1 ratio. So if you draw a curve of capacitor versus the reverse voltage, you get this curve. Varactor modulators, this is our first thing after the diode, where we'll be using that. Here, this is a circuit diagram. Firstly, we are using L1 and the D1. These are the D1, that is our varactor diode form the tuned circuit. This is called tuned circuit. C1 couples with the tuned circuit with the oscillator. Here C1 is also present, which couples with this tuned circuit. Next, R4 sets a fixed DC bias to control the center frequency. Here is our R4, which does this work. Now we have message signal is applied to the C5 via and RFC via microphone. Here we are applying our message signal. It gets amplified. It is sent to the C5 and RFC. RFC is radio frequency choke. So signal adds or subtracts from the reverse bias. It changes the varactor capacitance. So this gets changed and hence our FM is produced. So if there is a positive signal, then there will be a lower capacitance, so higher frequency. If there is a negative signal, higher capacitor, so lower frequency. Based on that, you are having a problem. You can do it. Then LC oscillator, what are its limitations is it's actually unstable. That is, it is affected by the temperature and voltage. FCC need high frequency stability. Crystal oscillation is performed. Next is FM using the crystal oscillator. We learnt about varactor. Now here is crystal. We are using a crystal here, placed here. So frequency can be pulled by placing a varactor in a series with the crystal. This is placed in series with that. There is a small deviation possible. In this case, it is suitable for the NBFM system, not for the WFM. NBFM means narrow band frequency modulation. WBFM is wide band frequency modulation. Frequency multipliers, here we are having a crystal and we are having various frequency multipliers, hence we get the frequency. This is used to increase the frequency of the carrier and the deviation frequency. FM signal is applied to the multiplier, so multiplies both frequency and the deviation. A frequency multiplier circuit is one whose output frequency is same as the integer of the multiple of input frequencies. Next comes our important concept, that is voltage controlled oscillators, or you can say VCOs. So here oscillator whose frequency is controlled and is controlled by an external input voltage is called as an voltage controlled oscillator. A special type using a crystal, where we use voltage controlled crystal oscillator VXO. Here VCOs are used for the frequency system. We have PLL, any voltage to voltage conversion as the application. So discrete versus integrated VCO. Discrete is still used in the VHF and UHF and microwave. Integrated, we use silicon, germanium, CMOS and VCOs. Here we'll be discussing about silicon germanium based high frequency VCO. For this, the circuit diagram is very easy. Write on to Q1 and Q2, cross couple them here like this, cross couple them. Place a diode, vector diode D1 and D2. You will be having two inductors then that is connected to the VDD, and here it is downside, it is connected to the current source. Place another one transistor Q3 and Q4 in the outer part. So this is our this is our silicon based high frequency VCO. So this is built using we use silicon germanium bipolar transistors, that is Q1 and Q2, in a cross coupled multi vibrator, that is flip flop configuration. So frequencies determined by the inductors and D1 and D2. Inductors are spiral metal tracers on the chip. Diodes are reverse biased to vary the capacitor. Input is we give the modulating signal, that is control the voltage at the junction of D1 and D2 used in the FSK. Then output is two complementary sine waves from the emitter follower, that is from the Q3 and Q4. Tuning range is given. So CMOS based on the VCO for the wireless communication. This is another one simplified diagram of the above. It is the same but uses a cross-coupled LC resonant circuit design. Operates on this range, that is for that range, and this is for this range, smaller range. Variations used in the Bluetooth transceivers and wireless LAN applications. Low frequency IC VCO. So here for the lower frequency we use IC. So include an RC multivibrator type oscillator controlled over a wide range by an AC or DC input voltage. Typically have a wide range which is less than 1 Hz to approximately 1 MHz. Output is either square wave or triangle wave here, not a sine wave. So here we are using any 566. So external resistance R1 is given to the 6th pin of the any 566, sets the current value for the internal current source. Capacitor C1 at the P7, this is our C1, is charged or discharged linearly. External voltage is given at the pin 5, varies with the amount of current from the current sources. Schmidt-Trigger circuit switches the current source based on the capacitor level. Here we are having Schmidt-Trigger circuit. Next is a linear sawtooth voltage develops across the C1 and buffered output at the pin 4. So we get buffered output at the pin 4. Schmidt-Trigger output is a square wave at the same frequency available at the pin 3. For the sine wave output, triangular wave is filtered with a tuned circuit. Next is compare frequency modulator circuit. This is the second part. That is, current sources is biased with the voltage divider R2 and R3. Modulating signal is applied through the C2 to voltage divider at the pin 5. The capacitor between the pin 5 and pin 6 prevents unwanted oscillators. Center FC is set by the R1 and C1 values. FC is up to 1 MHz, can be used for higher frequency or deviation. Output can derive the frequency multiplexers. Modulating signal can vary FC over nearly 10:1 range. Deviation is linear with respect to the input voltage over the entire range. Next topic is frequency demodulators. So here Frequency demodulament is any circuit that will convert the frequency variation in the carrier back to infinite voltage variation and can be used to demodulate or detect the frequency signals. Circuits used to recover the message signal from a frequency transmission is called as an demodulators, or you can say detectors. First is slope detectors. It is the simplest frequency demodulator used of tune circuit and a diode detector to convert the frequency variation to voltage variation. So this is the circuit and this is the slope we are getting. Next is similar to the amplitude detector as we have studied previously. So L2 and C1 form a series resonant circuit. You can observe here L2 and C1. Where voltage across the C1 peaks at the FR. Next is circuit is tuned, so FM carrier frequency FC is on leading edge of the response curve. As FC varies lower frequency, then we'll get lower output across the C1. Higher frequency, we get higher output across the C1. Voltage across C1 is rectified into DC supplies across the load R1 and filtered into varying DC signal representing original message signal. What are the drawbacks of this detector is it requires precise tuning. Nonlinear response causes the amplitude distortion at the wide deviations. This is not used in practice but demonstrates the frequency demodulation principle. Our next important concept is phase locked loops. PLL. So this is a frequency phase sensitive feedback control circuit used in the frequency demodulation, frequency synthesis and various filtering and signal detection applications. Here this is our circuit. We are giving an FM input here and we have a phase detector. We have low pass filter. Our error signal is given and we get a recovered message signal. Also, a feedback is sent to the VCU and it is sent to phase detector. Primarily, what is the function of this phase detector is it compares the two input signal and generates the output signal that when filtered will control the VCU. If the difference of the phase and the frequency between the input frequency modulation and the VCO signal, the phase detector output varies, which is directly proportional to the difference. So the filtered output adjusts the VCO's frequency in an attempt to correct for a original frequency, or you can say phase difference. This DC control voltage is called as an error signal, which is fed back. When there is no input, then the phase detector and the low pass filter output are 0. The VCO then operates at which at that stage it is called as an free running frequency. Its normal operating frequency as determined by the internal frequency determining components. When the input signals are close to the frequency of the VCO is applied, then the phase detectors compares the VCO, that is free running frequency, to the input frequency and produces an output frequency which is proportional to the frequency difference. In the phase detector, the output is a series of pulses that vary in width in accordance with the amount of the phase shift, or you can say the frequency difference that exists between the two inputs. If the input is filtered into a DC voltage that is applied to the VCO, then such that it forces the VCO to move in a direction. It forces the VCO to move in a direction that reduces our DC error voltage. So what is this DC error? The force VCO frequency to change in direction that reduces the amount of phase and the frequency difference between the VCO and input. So at one point, what happens is error voltage causes the VCO frequency equal to the input frequency. When what happens, the PLL is said to be in the locked condition. Now the VCO in a PLL therefore is capable of tracing the input frequency over a wide range. A range of frequency over which a PLL can track an input signal and remain locked, it is called as a locked range. So it is usually a band frequency above and below the running frequency of the VCO. That is called lock range. If the input signal frequency is out of the lock range of the PLL, will not lock, then it will not lock. So that VCO output jumps to its free running frequency again. So the phase detector determines the phase difference between the free running and the input frequency to the VCO, and it will generate the error signal that forces the VCO, which is equal to the input frequency, which is called as a capturing of an input signal. PLL remains locked and it will track any changes in the input as long as the frequency is within the lock range. So the range of frequency over which a PLL will capture the input signal is known as a capture range. So this is narrower than the lock range. So I will explain here. See, this is our F0, that is VCO free running frequency. So capture effect will be greater than that, then lock range will be greater than that. So these are the different frequency signals, and here in that, if we are having the same frequency, the capture phase is here. So after that, you have to write the circuit where PLL FM demodulator using a 565 IC. This is an IC. You can observe 2 pin, 3, 4, 5, 1, 9, 8, 10, and 7. These are the pins of that IC, and this is how happens in case of IC. Next, we will go with the communication receivers, that is superheterodyne receiver, an important concept and an expected question. Here, a sensitive and a selective receiver can be made using only amplifiers, selective filters, and a demodulator. This is called as a radio frequency TRF receiver. So this does not usually deliver a kind of performance expected in modern communication application. One type of receiver that can provide that performance is our super heterodyne receiver, which will convert all the incoming signals to a lower frequency, or you can say intermediate frequency, at which a single set of amplifier and filters is used. Most of the gain and the selectivity of this receiver are obtained by the IF amplifier. The key circuit is here the mixer. Actually, main part is mixer, which acts as a simple amplitude modulator to produce a sum and the difference frequencies. Incoming signal is mixed with a local oscillator signal to produce this conversion. We use this antenna incoming signal RF amplifier. We have a mixer which is fed with the local oscillator or the frequency synthesizer. So that is sent to IF amplifiers are there. After that, it gets amplified, and that goes to the demodulation where we are having AGC is also there, and finally the audio output, and that is sent to speakers. This is called as communication receiver. So RF amplifier, here we'll explain one by one. RF amplifier, the antenna picks up the weak radio signal and it feeds to the RF amplifier. So it is called as low noise amplifier. So this provides some initial gain and selectivity. They are sometimes referred to as a pre-selectors. Tuned circuit help the desired signal or the last frequency range in which the signal resides. So tuned circuit is fixed. Tuned receivers can be given a very high Q so that excellent selectivity can be obtained. In receivers that must tune over a broad frequency range, so selectivity is somewhat more different to obtain. Antenna connects directly to a tuned circuit at the mixer input, providing a basic selectivity. Now the RF amplifier, it enhances the sensitivity via a gain, selectivity through a added tuning, and signal to noise ratio is enhanced. So this also better rejects spurious signal, reducing the mixer generated interface. Now this addition of the RF amplifier, this will limit our local oscillator radiation. Without one, local oscillator signals can leak the antenna and radiate, potentially interfering with nearby receivers. And this was all about RF amplifier. Here we can use what is bipolar FET transistors we can use. Then mixers and local oscillator. The output of this RF is given as an input to the mixer. Mixer receives an input from the local oscillator and the frequency synthesizers. So output of mixer is input signal and the local oscillator and sum and the difference frequencies of the signal. Usually this tuned circuit at the output of the mixer selects the different frequency intermediate frequencies. The mixer may be a diode, a balancer, a modulator. Now the local oscillator is made tunable so that its frequency can adjust over a relatively wide range. We use IF amplifier. This is the output of an IF amplifier containing the same modulation appeared as on the input of the RF amplifier. So the signal amplified by one more IF amplifier. We have one more one, and most of the receiver gain is obtained in these stages. IF frequency are usually lower than the IF signal, usually approximately 455 kilohertz. Demodulator, here highly amplified IF signal is finally applied to demodulator detector, which recovers the original modulating information. Demodulator may be uh, AM or of an FM or SSB. Automatic gain control AGC. This is an output of the demodulator is usually an original message signal. The amplitude is directly proportional to the amplitude of the received signal. So recovered signal is rectified and filtered into the DC voltage by a circuit called AGC, that is automatic gain control. This DC voltage feedback to the IF amplifier to control the receiver gain. Now AGC helps to maintain constant output voltage level over a wide range of RF input levels. So amplitude of this RF signal at the antenna of a receiver can range from a fraction of it has many dynamic range. With the AGC, overall gain of the receiver is automatically adjusted depending on the input signal level. Frequency conversion, what happens here is process of translating the message signal to a higher or lower frequency while retaining all the originality of the transmitted signal in information. If the radio receivers, high frequency radio signals are regularly converted to a low IF, where improved gain and selectivity can be obtained down conversion. This satellite communication, in the satellite communication, the original signal is generated to a lower frequency and then that is converted to the high frequency for the transmission for the up conversion. Mixing principle, what happens here is frequency conversion is a form of AM where analog connection is carried out by a mixer, circuit or converter. The function is performed by a mixer called heterodyne. We give an input signal, we have a mixer which gives addition or the subtraction of the signals. Now we have local oscillator, tuned circuit or the filter which finally gives out the intermediate frequencies. This is a concept of mixer. It has two inputs. One is from input signal and another is from local oscillator. So signal is transmitted into a simple sine wave or any complex modulated signal containing the SP. The output of this mixer consists of an Fs, F0, F0 plus Fs, F0 minus Fs. So local oscillator frequency determines the new frequency. A tuned circuit is used at the output of the mixer to select the desired signal. JFET mixer, an important one. Here the FET makes a good mixes because they provide gain and have low noise and often a nearly perfect square law response. So FET mixer is biased so that it operates in non-linear portion of its range. Input signal is applied to the gate and local oscillator signal is coupled to the source. Again, tuned circuit is drained, selected and different frequency. You can observe this is our N channel JFET. From the antenna of the RF amplifier signal is given. So VDD is present and here 2 IF amplifier. One of the best characteristic is drain current versus the gate voltage curve is perfect square law function. With the perfect square law mixer response, only second harmonics are generated. So in addition to sum and different frequencies. So this was all about the end of the module 3 part 2. Hope this helped you to understand the notes and exam focused topics better. All the previous modules are linked in the description box. So feel free to go back and revise. If you found this video helpful, please like it, share it with your friends and don't forget to subscribe to Exam Ignite to stay updated with the upcoming videos. Thank you for watching and see you in the next video.